Hello everyone, in our project we are working on the problem of music source separation. Like when you listen to some song, we usually hear a mixture of multiple sound sources at the same time. It can be drums, it can be vocal, it can be some guitar and something like this. And our goal is to take this mixed signal and automatically split it into separate components. So the first step is to describe what is audio signal is. Mathematically, every audio signals we represent like some function y equals to x of t, where x of t represent our signal, our audio signal, t represent the time, and y represent the amplitude of our signal. And because this is the continuous function, on the graphic we will get something like this. Here we have time, here we have amplitude, and something like this, something like a waveform. Okay, the next step is sampling. Because the computers cannot directly work with a continuous signal, we have to convert analog signal into discrete one by using sampling. Sampling means that we measure the value of a signal at the specific time intervals of continuously. The time interval between two samples can be written like some delta t equals to 1 divided by some sample frequency. For example, we can take some sample frequency like 32,000 Hertz. That means that the signal is measured 32,000 times per second. Okay, the next step is discrete signal. As I said, computers cannot work with this continuous function, so we have to create discrete signal. Discrete signal is written as some x of n, where n is a sample index. So in the practice, we will get some large sequence of x0, x1, x2, and go on. And each of these numbers represent the amplitude of the signal as a specific time. So the next step is STFT, or a short time Fourier transform. After we obtain this large sequence, we can analyze its frequency content, and for that we can use short time Fourier transform. And the mathematical expression of this method looks like x of some mk equals to sum from minus infinity to infinity xn multiplied by w n minus m multiplied by e in the degree of minus 2j p n k divided by large n, where xn is our signal, our discrete signal, and v of n minus m is a window function. What is a window function? Like basically in FST we analyzed only some segment. So, and for each segment we apply window function. The purpose of this window function is to smoothly reduce the signal amplitude near the edges of the segment. Now, if we cut some segment suddenly, it creates sharp edges in the signal, and these sharp changes distort the frequency spectrum. This phenomenon is called spectral leakage, and the window function helps to reduce this problem by smoothing the boundaries of the segment. So after we apply STFT, audio signal is transformed from the time domain into time frequency representation, called a spectrogram. So basically we will get some time. Here we'll have frequency, and here we will have some cells, and each cells of this graph represents the energy of the specific frequency at a particular moment in the time. So if the cell is darker, that means more energy. And this spectrogram can be represented as some matrix where numbers were described as a power in all these cells. Go on. And the row of this matrix correspond to frequency beams, and the columns correspond to time frames. So once the signal is represented as a matrix, we can apply some linear algebra techniques. First techniques is PSA, principal component analysis. After the signal is transformed into a matrix, we use the PSA. PSA analyzes the variance in the data and finds direction when the data varies the most. So firstly, we compute some covariance matrix multiplied by m, x transpose multiplied by x, and then we solve the agent problem. Where v is some agent vector, alpha is some agent value. And the agent vector represents the principal direction of variance in our data, while the agent values indicate how much variance exists along those directions. Okay, the next step is SVD, or singular varied dimension decomposition. Like for example, we have some matrix X, and the SVD of this matrix can be written like this. You have some U multiplied by sigma multiplied by V transpose, where U contains the left singular vectors, sigma is a diagonal matrix, diagonal matrix with singular values, and V transpose is a right singular vectors. These singular values describe importance of each component of the matrix. By selecting only the largest singular values, we can approximate the matrix and reduce noise or less important components. So basically, both of this method can help us to separate the dominant patterns in the audio signal, such as the vocals and instrumental parts. So that's all. Thank you for your attention. Goodbye.